So for our invited talk, it's my great pleasure to introduce Nathan Kutz. He's a chaired professor in applied mathematics at the University of Washington. Nathan received his PhD degree in applied mathematics from Northwestern University in 1994 and has been on the faculty at the University of Washington since 1998. He's a leading expert in many different areas of applied math, including machine learning, scientific computing, dynamical systems, control theory, and so on. He was an early visionary in seeing the power of combining data-driven scientific machine learning with physics-informed dynamical modeling. Recently, he has really been pioneering doing pioneering work in data-driven discovery of nonlinear systems. For example, you may know his Cindy method and other great papers in this line. So I'm really excited about this talk, and please help me welcome Professor Kutz. Nathan, please unmute yourself, share your screen, and we're looking forward to this talk.
All right, thank you so much. Let me get my slides up here. Hopefully everybody can hear me fine. So thank you all for attending, and it's a pleasure to be here. It's fun to interact with some of my colleagues and see them here, and even though it's not live, it's over Zoom. I wanted to just share some thoughts here about thinking about deep learning methods that we can use for, I'm going to focus on just thinking about discovery of dynamics as well as coordinates sort of as a joint effort. And this work is all done with Steve Brunton, who's my main colleague here at the University of Washington. And I'm very thankful to Princeton University for the support in hosting this. I will say that I am an alum as a postdoc from the program in Applied and Computational Mathematics. That was a while back. And more recently, Steve got his PhD there in Princeton in the mechanical and aerospace engineering. So we're representing Princeton in some sense too. So let me get right to where I want to take our mind, which is this structure here. This is going to really pervade the talk, this kind of architecture that you're seeing here. And I think a lot about this is a very targeted use of neural nets, which is I'm going to take my data. What I'd love to do with that data is talk about thinking about training the neural network to give me a good coordinate system. Now, I recognize that good coordinate system is a very subjective term. So I'll try to dig down on that a little bit and talk about what are the diversity of things you could think about in relation to a good coordinate system. And then once you're in this new variable set, now you're going to prescribe dynamics in there. Okay, and then you build yourself a pathway back out to your original measurement space, whatever that is. I always like to say that just because you measured it doesn't make it the right variable. And I think that's an important fact. A lot of what we have are sensors that are everywhere that measure lots of different things, but they may not be the right intrinsic coordinates that you should be using. So the question is, can you take these really rich data measurements and sensors that we have today, whether it's vision, infrared, LiDAR, and map yourself to a coordinate system which is more useful for dynamics. The other thing I want to talk about is you see the pinch down structure here. It is an autoencoder, which is I really want to get down to the intrinsic coordinates and dimensionality of your dynamics. So that's what we want to think about there. Okay, so what can we do to reduce coordinates? Well, look, this is not new. We've been doing this forever. Most of the 20th century, if you look at a lot of math physics, we learned a lot of special functions, whether it's Bessel functions, Hermite, Laguerre, depending upon the geometry of the dynamics, we often found there was a very nice set of basis functions to represent your dynamics in. And I think all of us are aware that there's really nice ways to represent things in the good coordinate systems. Maybe we used expert knowledge as well. And sort of really more recently, we've started thinking about SVD-based methods. So reduced order modeling techniques think about taking the data, using SVD to find a low rank subspace in which to project your data. And this goes under different names: POD, which is the proper orthogonal decomposition, PCA, EOF, Houghton transform. They're really, with minor details, they're all kind of the same. They're SVD-based drop downs into some subspace. And you can also use neural nets. And so this represents almost a historical progression there about how can I get myself to a coordinate system, and really with the idea of reducing rank and doing some things there. So that's what we might do on that coordinate transform. Now the dynamics themselves, so we have some spatial temporal data. That's normally what I want to be looking at. I've made a transformation to some subspace, and now I have time series data in this low rank representation. And what are the things I can do there? Where, you know, what we've typically done with time series data, I'm just throwing out something like that's classic, like ARIMA. But there's also modern techniques like dynamic mode decomposition, Koopman decompositions. We also can do this Cindy architecture, which I'll talk a little bit about, which is sparse identification nonlinear dynamics, can be ODEs, PDEs. You might even crush this down into a normal form, or even just, I have time series data, put it into LSTM, GRU, whatever you want to do there with another neural network architecture, if you'd like. So these are the kind of things that we want to think about, which is coordinates and dynamics. And notice I've separated them, but when I actually come to do these things, I want to train these things jointly to arrive at some things I want to do. So most of the stuff I'm going to talk about is super subjective. So I understand that all of us have different viewpoints about what this might mean. And that's okay. So you're just going to get one representation of what that might mean, right? I have a doctor of philosophy, and so I'm going to philosophize in my own viewpoint on this a little bit. So I want to talk about good coordinates, and I'm going to come back to the title slide here. And this is the retrograde motion of Saturn and Mars. And this is the classic problem of physics. In fact, I would say this was physics for, you know, many, many centuries, from the time of Ptolemy all the way to Newton. You know, we were trying to understand the motion of these planets. What were the kind of governing equations? And so you see, when you observe from the night sky, you could, of course, come up with a theory for this. And in fact, Ptolemy did. The alchemist lays out the foundations of circles upon circles, which is this earliest Fourier transform you want to think about, which is you just look at the mapping of this as just a circle upon a circle upon a circle. You get the right periods out. It's a Fourier decomposition and a very accurate way to do forecasting of planetary motion. Okay, now that was all done in a coordinate system in which the Earth was the center. And this is why you see this motion. However, things changed, right? So by the way, this is the doctrine of the perfect circle. It's probably, I'm going to say it might be one of the theories that lasts the longest ever in history. You know, it's about 1,500 years. Very few theories can stand up that long, right? Most of them stand up a couple decades, maybe a century, and then someone comes and knocks them down. It took a long time for this one, and at great cost, by the way, to the individuals. And really, we start thinking about Galileo changing this viewpoint and paying a heavy price for suggesting that the heliocentric universe might actually be the right coordinate system. This was built on by Kepler. And I would argue that the main thing that this does for us is that once you establish this heliocentric coordinate system, in other words, once you change the coordinate system, now you pave the way for F equals ma with Newton. And so now, because you have the right coordinate system to represent that dynamics, and of course we know that Newton wasn't quite right, because we started getting measurements that were inconsistent with that theory, leading to basically building out general relativity. And so there should be more pictures coming, right? As we get more refined measurements, we're going to find out that, you know, Einstein wasn't quite right, and here's the new theory. So these are all important things to start thinking about. So I think about this process as you discover first the right coordinate system, which is heliocentricity. Then you can discover your F equals ma, and the two have to kind of come together. Now, what's interesting about this is this represents something, I think, deeper for us from the mathematical point of view about your viewpoint, potentially. I think about Kepler and Newton, and in some sense, even though Newton had F equals ma, really what he produced were ellipses as these solutions, which really were the same solutions that Kepler had, right? So you could say they both had theories that were equally good, right? And Kepler's was fitting of data. Newton had a concept there. Now, the important thing that what Newton was able to do with F equals ma is generalize. With this understanding of planetary motion, you could actually compute what would it take to launch a rocket from the Earth and land it on the moon. Whereas Kepler fit to observational data and did not have that ability to extrapolate outside of that data set. By the way, there's a natural place where both these schools of thought can be very successful and are in our current day culture. And here is where it is. So let me just show you these videos, and maybe you've seen things like this. And on the top, you have this robot. This came out in just the winter, which is from Boston Dynamics. This is incredible feats that this robot is doing, actually. And on the bottom, you have a self-driving car driving through, bad terrain, around obstacles. It's quite impressive, both of these. Now, these are sort of, in some sense, I would say, the state-of-the-art grand challenge problems of today: robotics, self-driving cars. And in some sense, this reflects up top what you have is sort of a Newton idea, because that's all physics driven, heavily physics driven. That robot has F equals ma everywhere in it. Whereas the bottom, that self-driving car, bank of sensors, lots of data, lots of labels. That's how it's getting around. It does not have knowledge of physics. And this really reflects on the bottom left there. There's a comment there by Bryman, The Two Cultures. Bryman wrote about this, right? He really talked about sort of this statistical versus machine learning cultures of building models versus building accuracies. And so this is just a very, rough sketch of this. And I'll just tell you, both are very successful. You can't say one's better than the other in many ways, because they both have merit in different application areas. Where this talk is going is the top. I really want to sort of stick with the physics-based ideas, which means I want governing equations out, and I want to be able to learn these things from data. Okay, by the way, this idea of coordinates and coordinates and equations jointly, it sort of pervades everywhere. So I just want to show you here a slide of reduced order modeling. I know some people here do quite a bit of reduced order modeling, but the first line of equations there is like some generic PDE. And normally what reduced order modeling does, this is sort of the paradigm, is you say, I will take snapshots of the evolutions of my PDE, find a low dimensional subspace, which is you usually do it with an SVD. You find the first R modes, and you project into that space. And so now what you have on the bottom is a Galerkin projected PDE now dropped into an R dimensional space. So you can see there's this process of coordinates, dynamics that come out of this. So it's exactly the same as the planetary motion. Same thing here, another example. And again, we're all highlighting this idea of the joint discovery issue, which is the top of what you see there is Berger's equation, is one of the first nonlinear PDEs I ever looked at, and for probably it's true for most of you. But what's remarkable is that Cole and Hoff independently in around 1950 discovered this transformation. There it is, U equals. And in this transform variable, this Cole-Hoff transform, you turn that nonlinear PDE into a linear PDE. So one way to think about it is, why would I work with the U framing? Because if I move into this V coordinate system, I can write down all the solutions by pen and paper, right? There's something really powerful about being able to linearize this. And this concept, there's very few PDEs you can do this with, but there are many that you can. And the inverse scattering transform also represents this philosophical step, which is you think about Peter Lax and coming up with these Lax pairs about for governing PDEs, where inside of those operators is the compatibility condition between those operators gives you some evolution equation U, which is your PDE. And this is typically done for completely integrable systems like KDV, NLS. And so it's got this rich history of a coordinate transform in which in that new coordinate, things evolve linearly, right? So there's something very attractive about that. So let's get to the mathematical formulation of what we want to be doing here. And this is it here. So I want to think about two things that are happening. I have some dynamics that are evolving, dx dt equals f. Now, what I actually have are just measurements of the system, y, and I don't know f. And I don't even know the measurement model h. I have noise on the system, parameters. So this is the problem generically I want to think about solving, okay? And so, you know, it's really extremely opposed, right? Because I'm going to take measurements alone and try to back out h and f and all the parameters. And how do I do that? Well, what we know about ill-posed problems, you just regularize. You just find, you know, you just go and say, I can't solve that. Put some regularizers on it. I can solve that. And I want to talk about that regularization process because that's going to be the key to the whole thing. So for us, regularization is going to be all about sparsity. And really, this is a proxy for what I think of as interpretability and parsimony. And these are old ideas, right? So we go back all the way to Occam and Occam's razor, Pareto. They're all saying the same thing. They're all talking about this idea of a smallest number of explanatory variables being what you want to do versus you know, they're really talking about overfitting in some way, generically, philosophically. And so what we want to do is bring this idea in as our physics regularization. And I think about that as the ultimate physics regularization because governing equations often have just a few terms that matter. We look at whether it's Maxwell's equations, Schrodinger equation, Navier-Stokes. These are PDEs describing many, many complex phenomena, and yet there's just a few terms to describe all of that. So that's what we want to think about for here. So let's first talk about just discovering governing equations. And this is where the Cindy architecture comes in, which is the sparse identification of nonlinear dynamics. So I want to find dx dt equals f. Well, what could f be? Well, we could make libraries of potential right-hand sides for that dynamical system. And so you come up with a library of potential right-hand side terms. This is like a basis. It's not orthogonal. In fact, that matrix data is pretty ill-conditioned. But you say, okay, here's all these terms, and this is a matrix A, and this is going to result in nothing more than just solving AX equal to B. Okay? And let me show you how this works. Now, here's an example. This is using the Cindy algorithm here, which is I take the model, which is let's say the true model is I give you X, Y, Z data. I produce X dot, Y dot, Z dot. That's B in the matrix AX equal to B. The matrix A is a library of potential dynamic terms. That's A. And then I just have to solve for X. So it's AX equal to B. And the goal then is when I do these loadings, I believe out of this library, there's only a few terms that should matter. So I just want to promote sparsity on the solution to that overdetermined system. Okay, that's it. And the way we promote sparsity, we don't do lasso. That's pretty unstable. And I think Kendez has recently showed that the pathway of lasso can be pretty unstable. We do a sequential least square thresholding technique, and out pops the balls there with that are lit up tell you which terms seem to be on, and in fact it gives you back exactly the Lorentz equation. So you can do this for data, and here's just a table of a bunch of PDEs that you can actually discover just from data themselves. And so you know, these are some, you know, good example problems from KDV to things like Kurmoto-Shibashinsky, which exhibit pretty complex dynamics, to Navier-Stokes, and so forth. So this is sort of the paradigm. You know, you propose a library, you select the terms that matter, that's your governing equation. Now, what's assumed in here the whole time is that I know the state space variable. And in fact, that's what I want to get around. So Cindy is there, and then this represents what I think really, which is the heart of this talk, which is, yeah, but what do you want to do with that? Well, here's what I want to do with it now, is I want to take this, and if I took data and I didn't know the state space, could I discover the state space and the governing equations jointly? And this is work that Kathleen Champion did. So she just graduated. She was a fantastic student, and she got this trained up. It's the reference of the paper there. And so the idea is to learn how to embed the dynamics in which the dynamics in that coordinate system is sparse. So it's tying in the Cindy architecture with an autoencoder. And there's the loss function. You just penalize the right things. I want to penalize the sparse dynamics. I want to make sure that my autoencoder shrinks down to the right coordinates, can reconstruct. train. And from doing that, you can do a very important experiment in my view, which is, well, here's some embeddings and what we can do. We could take the Lorenz, glue each of the XYZ to some spatial modes, non-linearly actually, and then ask the question, could I, from that time-space structure on the top left, could I first of all learn how to undo that coordinate transformation I did and get back Lorenz? You can. And the bottom one is the one that I like the most, which is if I gave you a video of a pendulum and you knew nothing about pendulums, what this is allowing you to do is it will take the video, which is pixel space, it's high dimensional pixel space, and over time in training, it will say, oh, I will learn theta theta dot. And then I will learn that in that variable, theta double dot is going to be sine theta. So when you look at a pendulum, you already know the right coordinate because you are super prejudiced about and biased because you've got education. But if you take a lot of these measurement systems we have, which are cameras, this thing's going to learn it for you. It's going to learn that that's the coordinate system and get out the structure. So I really like that in terms of a philosophical point of view, which is when you go to real systems now and you don't know the dynamics, you don't know the state space, this is a nice architecture to jointly discover those. All right, a couple comments. The training of the coordinate system is not generalizable, right? It really lives in the data set, like it's specific to the data set. However, the F=ma physics you get out of it, there's a good chance that that physics principle is generalizable. So it's interesting because if you were now to take a new system of the same kind of physics, you can lock the autoencoder dynamics to this dynamics you found and just learn new coordinates for that. So that takes some pressure off the neural network. Where I think this is actually going to be very useful is in discrepancy models. I mean, I think we know a lot of physics, so it's not like we come to systems and I know nothing. We often know things. And so what happens if instead of discovering from scratch, we start thinking about, yeah, but I actually know quite a bit. So I know that this is true. Like I might have conservation of mass momentum. I just need, but my model's not good enough. I'm missing some physics. How do I do that? Well, you know, the Cindy architecture is really easy to do this with because if you know f of x, you move it to the left side, that's part of your b now, and I just go after trying to find that g of x. And so let me show you where we've used this. Okay, so here we go. This is a pendulum and we try to place in the upright position. And so the top one, you have the Platonic model of the F=ma physics for that double pendulum, and you tell that cart, with that physics, can you stabilize it in the upright position? And it turns out, okay, sorry, I'm trying to get the bottom video to go there. And it turns out it doesn't stabilize it, but in the bottom, now you let it learn a discrepancy model. In other words, you have frictional forces, you have both on the thing, both on the joints as well as the air. When you learn those, a correction to that, this thing now, with that correction, can stabilize the pendulum, where if it just had the physics, the Platonic version of the physics, it cannot. And where this is really important is in this digital twin revolution we're going to undergo, which is how do I make virtual robots on a factory floor so I can basically have a virtual model of the entire factory floor. Well, you can't do it currently with your Platonic models. If you're doing precision manufacturing, the models we have are not good enough. And so what this will allow you to do is learn discrepancy models to make your robot actually behave, your model of the robot to be like the actual floor. So these are all nonlinear dynamics, but we can also push this further and say, well, I like linear models, not because, you know, for any other reason than I can write down solutions by pen and paper. And right, you can say so many things about linear dynamics. And so another way to go about this is to say, how about if we do what's called Koopman theory, right, is to basically learn a coordinate transformation to get me into a linear frame of reference, or where the dynamics is linear. And so this is work with Bethany Lush. And so what we were really after is, can I find that coordinate system that's going to put me into a new coordinate system where it's linear? Now, this is exactly like that Kohlhoff transform. I had a nonlinear PDE. The Kohlhoff transform takes me now to a linear PDE. So we want to do the same thing here. However, this problem is really hard, even for something as simple as a pendulum. So the concept is easy, which is move to a coordinate system. Like when I take steps in that coordinate system, it should be linear. But the problem is, how do you handle a continuous spectrum? In other words, you can do this only for a single oscillation amplitude of the pendulum, because every time you change of the nonlinear, the pendulum's nonlinear, and if you make the amplitudes larger, the frequency shifts. So if I want to keep the intrinsic rank in the middle to 2 degrees of freedom, I cannot do that unless I parametrize that frequency. By the way, it's very easy in the middle if I want to go to very high dimensions to parametrize all the frequencies, because you just say, yeah, just go to infinity, virtually in this middle layer. Don't pinch it down. Just live up here and get everything. But you lose a lot of interpretability when you do that. And frankly, the pendulum's still two-dimensional. Why would you build your physics in infinite dimensions when you know it's 2? But the only way you could do that is by parametrizing the frequency. So you have a side network to learn that as well. It took us a long time to figure this out, by the way. So really simple problems can be very revealing to you in this process. And by the way, here it is, the pendulum. Basically, what you're seeing up there, here's the phase portrait on the top. Let's go to the middle section, and you can see through my coordinate transformation, I can take this nonlinear dynamical system in this phase plane, turn it onto circles. That's the idea of this Koopman embedding. You can also do it for more advanced problems like fluid flow around a cylinder. You take this nonlinear dynamics. It's not even that very nonlinear, but even this is hard to figure out how to embed. We can embed it in a completely linear framework. All right. Finally, around this direction is neural networks for more general PD Koopman embedding. If I relax the middle there in the dimensionality, we basically were able to train these neural networks for generically linearizing PDEs. And for instance, what I'm showing you here is a linearization of the Kuramoto-Shibashinsky equation. So this is just like the inverse scattering transform, which allowed you to linearize a certain class of completely integrable PDEs. We've done this for burgers, for Kuramoto-Shibashinsky. And so you can train these neural networks. And one of the keys here is to use this drop the identity downstream for you, a lot like recurrent neural nets, because it really takes a lot of pressure off of the network to just start from scratch and figure out what it wants to learn. You start with the identity, and then you build around that to make these mappings. All right, so mostly what I've been talking about is neural nets for learning the coordinate transformation, but you can still use neural nets even in the time coordinate. And so what I mean by that is, suppose I'm in some subspace where the dynamics now is I want to model the dynamics that come out of the subspace. And the dynamics can look, here's an example. We made up some function. There it is. It's not just that simple, but it's, periodic or quasi-periodic. Well, what we can start to do is say, well, how about using just standard ideas of Fourier forecasting, which is, what if I project this into Fourier modes? That's what this second line here represents. I want to project it into a Fourier space with some frequencies, sparsely preferably, so we can penalize that. But also, if it doesn't look very Fourier-like, like the bottom one, what if I learn a neural net that will warp this thing to something that looks as sinusoidal as possible? So I'm going to have a training of a neural net to take quasi-periodic data, warp it into the smallest number of sine modes possible, sines or cosines possible, to be able to do long-range forecasting. In fact, we're really thinking about long-range forecasting here, because that's what a lot of these systems, that's what we want to be doing. So I just want to point this out, is we compared this Koopman forecasting idea across the board to all these neural network architectures, and they just work a lot better. And I'm not going to say that we're special. I'm just going to say that Fourier is pretty awesome. Like if you work in Fourier modes, they're not only interpretable, but like they're the only functions that live, you can go to infinity with them and they're not gonna blow up on you, right? So they're really a perfect basis. You just need to touch them up a little bit with a neural net, and they're gonna beat all these LSTMs, these GRU echo state. We compared it against these. So anyway, I love using more classical methods, but touching them up if you can. And that was on power grid data. And here it is for this ROM model that I've often seen in the reduced order modeling community, which is on the top, you see this full PD simulation. You look at doing a low rank projection of this in SVD modes, and you look at the time series. And then from that time series, it's really easy to fit it to these Fourier modes because there's not that many. And now you're not even running a model at this point. You don't have the instability of the projective Galerkin model. It just gives you a very nice reproduction of the dynamics. So where do we want to go with this? Well, so these architectures are pretty powerful for both time and space, right? So like you can learn neural nets to transform your spatial coordinate system so you can represent better the dynamics. You can also just say, you know, embed this in a lower rank subspace and instead train a neural network to help straighten out the time dynamics. What I mean straighten out, I mean Fourier guys, I just made that word up, but you know what I'm saying. You project it in a good way into Fourier modes, and these are different ways to think about how to represent your physics, especially for forecasting, especially for understanding some parsimonious representation. How does this work towards going to harder problems like multiscale physics? I do want to highlight that we have been pushing in this direction, and with the idea of saying, well, you know, when you look at multiscale physics, one of the characteristics, and you know, Waynon's on here, you know, he wrote whole review articles on heterogeneous multiscale modeling, right? You get different physics at different levels of spatial and temporal scales. And so how would you go about learning those and pulling those apart? So one of the things that we've been doing is thinking about exactly a hierarchical framework for basically recursively pulling out features at different levels of spatial resolution. So the interesting thing here is you start off with a coarse network that just learns very coarse dynamics. That's the level 0. That level 0 information is now going to basically, you're going to now train a network at a level down. It's going to be a lot like wavelet decomposition, in which you now refine by a factor of 2 and another factor of 2 as you go down this cascade of spatial scales. So it exploits a lot of the features of multi-grid methods and also transfer learning to build these models. Now, what's interesting is once you build these coordinate embeddings at the different scales, now you can decide, what do I want to do with what the time series looks like at these different scales? Do I want to do a Koopman model? Do I want to do a DMD model? Do I want to do some LSTM or some Koopman forecasting? You have some options there about what you want to do, but this is sort of this recursive hierarchy for just pulling these things apart for you in an automated way. And so that's up on the archive if you want to take a look. The other place where we've gone with this is I've been talking a lot about dynamical systems, but you can just do boundary value problems. So you just switch this out. This is the first picture, and instead of dynamics in the middle there, I put BVP. And here's what's interesting about what we've been able to do is what we've been able to do with this is start to discover governing boundary value problems using the Cindy architecture. So I take a boundary value problem, and what we do with this is if you are able, it's basically LU equals F or some nonlinear operator equal F. And the question is, can you back out those operators? In other words, the governing equations. And in fact, we can do that with that Cindy architecture. More importantly, and this isn't up on the archive yet, should be soon, is we can find coordinate transformations that linearize things, which allows you then to build a Green's function. The Green's function is this very powerful concept that, you know, was so heavily used in the last century because that's the fundamental solution. And now, if you're doing acoustics or waveguides and optics, Green's functions are just this really important instrument to build models. Because once you have the fundamental solution, all you have to do is integrate it against the forcing and you have the solution. We can do that by learning a coordinate transform into a space that's linear, getting the Green function in that linear space. And so you take a new forcing, run it through a neural net, hit it in this linear space, and I'll give you back what the solution should look like. Okay, so anyway, I'm going to conclude here. So basically, you know, I like the architecture up top. That's kind of my favorite going right now. You know, it's that architecture up top gives me a lot of flexibility to solving the math problem I show you there below, which is from measurements, give me back some models that I can be useful. And everything here is regularized by parsimony. In other words, sparsity. So I want a few terms of F. I want to be able to I want interpretability above all else. For the most part, we're not so concerned about like, how accurate am I? I think what we're really concerned about is, can I write down some model I understand? Oh, it's a few terms. It's got these parameters. Maybe I can move it into a new regime. In other words, generalizability. And I think this architecture is really important. And I think it really reflects this parsimony idea as sort of, in some sense, a really important physics regularizer that we have been using forever. And so we're just imbuing it now in these neural nets. And I'll stop there. Thank you guys so much.
Well, thank you a lot, Nathan, for this impressive talk. And it's been very inspiring to watch it. And we've received many questions, probably too many to go through. So let's
just give me the easy ones.
Yeah, let's jump right into it. So one question was, have you tried to learn the laws of gravitation?
Oh, that's a great question. I say, okay, so here's our dream. We would absolutely love. So I actually downloaded this one point, which is, when Tycho Brahe passed, right? So his notebook went out. So now from Kepler, you really want Kepler's data, right? And he wrote this up in his book, but it's all in tables in a PDF that's scanned, and it's not. It would take even a very compliant grad student would probably not want to import that data into some, digitize it. But that's what we would love to do, is like take that data, put it into columns of positions, and then do that automated regression. More than that, we would love the data around even the GR data that Einstein had, right? The inconsistencies between F equals ma, which led to really discovering general relativity, was based upon data. And we would love that data. But I mean, for those of you who've worked quite a bit in data, right, it's one thing to say, oh, that data's out there. It's another thing to actually get it in hand. And that oftentimes is a massive, it's a frustrating thing, because once we get, but there's more and more data coming online. So eventually, I think some of that will be made over, and then we can actually analyze it. But yes, we'd love to do it. We haven't.
So maybe along that line, rather than using a poor graduate student, why don't we have a capture technology for doing that?
Yeah, exactly. Yeah, no, in fact, even the retrograde motion, it's a nice picture. You can pull out quite a few snapshots. And one of the things that's interesting about Cindy, and there's many things wrong with Cindy, not wrong, they make it difficult, right? Noise, in fact, if you have small amounts of noise, we can handle it. Rachel has actually done a really nice job, along with Hayden Schaefer, on if you have corruption of the data, you can still use that architecture nicely. But there's a lot of things that make it difficult. And normally what we need is, like all these neural nets, and you still need lots of data. And but you're right, the retrograde motion, if you could just pull those out and automate that, which seems like, again, you could probably do that. You need still someone to write that computer vision code.
Awesome. Maybe we have someone here on the call that can do that. Another question that I'm excited to ask would be, so you mentioned the instability of the lasso path, but that's been news to me, at least. So can you elaborate on this a bit, or maybe?
Yeah, I would. I was just going to point you to Candez's paper. I think it came out last year. Okay. So he does a pretty careful exploration of this in terms of, the skinny on this is that basically early on it makes mistakes. It drops terms that should have not been dropped. So by the time you get down to really pruning and refining, the terms you should have kept are gone. I don't know, Rachel could probably comment much more intelligently on that than I can, but I know that
I asked the question, Nathan.
Oh, you did? Oh, yeah, no, that's the only thing I know is reading that paper is that it's like, oh, Candez showed this. So I know I like to hold that up, because like, if he said it, it must be true. So, but we actually did explore this a little bit with some other problems. So one of the things that we actually did is we've worked a little bit on a sparse regression technique we call it SR3, for sparse, relaxed, regularized regression. So we reformulate the sparsity problem in a relaxed way. So in the relaxation, one term takes care of fitting, the other term takes care of sparsity, and then you make them proximal. And in fact, there's so much pressure on one variable to do both. But once you relax it, it's amazing how well this thing works. So we have a paper on this. It came out on IEEE Access, and one of the things we compared it against was lasso, some matrix completion problems, compressive sensing, and TV regularization, and it's kind of beats all of them pretty handily, actually. And that's just not, it's just because of the structure of relaxation makes it much easier for it to get stable solutions.
Okay.
So that's what we're starting to use now in this architecture, is to say, hey, this is a really nice way, robust way to get us the sparse solutions. And so we've been doing that.
That sounds awesome. So thanks for the references also. So now I have a few tough questions about when things go wrong. So the first one is, so say you have only partial observations, and from that, and those are insufficient to get the original dynamics. Would we still get something that at least would give us meaningful predictions without, I mean, for sure, I would give up on identifying the correct system, but could I still get a good predictive model?
Yeah, actually, thank you for asking the question. So this is really important, because one of the things that we're trying to go for here, and I just told you, is suppose you don't know the state space. You got measurements and you're trying to discover everything. But how do you even know you've measured enough stuff, enough information to get your X out? So one of the approaches that we've taken and that we're still working on, and this is about getting to the latent variable representation. Do you have enough space? Do you have enough there to get that? And so what we've been starting to do is take the time series data and starting to time delay embed it. And in the time delay embedding space, you get a shadow of the manifold of the full R-dimensional subspace. So what we use is the time delay embedded coordinates to pick up the latent representation. So we've had some success with this. I think it still needs a lot of extra work, but it is actually, these goes back to the classic ideas of the 1970s, really, about time delay embeddings, right? And there's some nice theorems there about this basically producing a diffeomorphism, the diffeomorphism away from the true dynamics, under suitable conditions. And so what we're trying to do is say, well, if we use time delay coordinates, we are going to have a better shot at getting the missing variables that we didn't measure. And so that's how we're approaching it. I think the jury's still out at how successful we'll be, but in a lot of the models we've looked at, it's actually pretty promising. You certainly get a lot more information than if you don't time delay embed, for sure.
Okay, so then we're looking forward to seeing more in that direction. Along the same vein, so what happens if I don't have the right terms in my dictionary? Is there any way I can, the method can give me a warning, something went wrong, or what will happen?
Yeah, so that's a great question. So I think what I like to think about, what happens in that case, and we've played around with this quite a bit. I don't have any rigorous statements to make about it. However, I'll tell you some observations. The observation is the following. If you have something that's very simple, like you have a library of terms, and you're missing the right term, you won't get a sparsity pattern out. What will happen is, if you're missing the right physics, it tries to compensate by using the other terms to sort of almost build a Taylor series expansion for representing the term you should have had. So when you look at this thing, if you see that it just won't sparsify, typically that's a signature that you're missing the right physics. We have been working on techniques to automate building richer libraries. So genetic type algorithms, which is you start with a library and how do you refine it to make sure that you're building out the right terms. And so that it's clumsy only in the sense that, when you put a genetic algorithm on anything, it's going to be slow. And, Cindy's pretty fast. You just, it's A equals B. But then once you start that machinery, it's like, now it's going to slow this process down and do lots of generations and things like that. But it's a way to go about that.
So I think that's great. So sometimes we rely on our human capability to figure out how many terms would we expect,
yeah,
and to have some common sense there. And maybe a quick question to the end. So the neural networks that you train in the PDE Koopman, can I think about those as being heavily over parameterized, or is there any insight also in that training?
Yeah, so that's a great question. I always struggle with the concept of.
Well, it comes from Rachel. All of her questions are great.
Yeah, I struggle. Yeah, I struggle with the concept of over parameterization from the following point of view. If I give you enough training data on a Kurmoda-Shevchenko, this is a little bit like even ImageNet. Like, if I give you so much information, so many initial conditions, so many of the dynamics, yes, my model is over parameterized, but I've also built a model that's seen everything. You can't show me anything out of that model. So I always feel like I struggle with this concept of over parameterization, even in computer vision. If I give you a large enough vision database, you know, say, oh, I trained it and so it won't overfit. What do you mean you won't overfit? I can't even give you a picture of a cat that you don't have one that almost looks exactly like it. You don't even have 1,000 that look exactly like it. So is that overtraining? Is that overfitting? You just have so much data that your landscape of where you live, there's nowhere you can be where it's not filled in. And in some sense, the same thing's happening here. You give it enough initializations, enough data, you've basically built a landscape. So as long as I live anywhere in there, I'm gonna get it.
So there was this couple of slides that you showed about, you have the physics and then you have a discrepancy. So you know some of the physics and some of them you don't know. And the question here is related to that idea, and asks about how does that knowledge of the physics relate to or inform the neural network architecture or the design of the coordinates. Is it helpful? Can you exploit that, or would you still use like the same approach you would use for completely unknown dynamics?
Yeah, so I you know, for at least this is an interesting question, right? Because I think that for the known physics, at least if you go down the road of trying to do this Cindy architecture of regression, in your library ahead of time, you know that I already know a certain number of these columns are going to be active because, you know, I know I have this physics or that physics. So the Cindy architecture is really nice about allowing you to bring in your pre-existing knowledge of the physics. The interesting, so that's easy if you have the state space and you just start trying to figure out, I'm missing some physics, how do I do that? But there's still the assumption that I know the right state space measurement variables there, right? So it's assuming that not only do I know some physics, but I also know the right state space. Mm-hmm. We haven't really, so in that context where we've, you know, come up and said, let's build a model. So there's a lot of different ways to handle discrepancy. Some people use these Gaussian process regressions to just sort of say, let's just, you know, whatever, learn some statistical distribution of this thing. You can also do even like Koopman or DMD type models. You can also try to regress to see, yeah, but if the one thing I don't like about GP, maybe I could say it this way. Here's what I don't like about GP. And in fact, I'm going to say this about learning paradigms in general that bother me a little bit. In Kalman filtering. So sorry, that was a lot of stuff I'm going to complain about. It's not really that big a complaint. But one of the things that about a Kalman filter is what I think of a Kalman filter is very much towards this idea. I have a model, I have data. They're different and there's a discrepancy. The thing that's dumb about Kalman filtering is even though I've been running this system for a very, very long time, my model never says, you know, I'm always off from that data. And you just always assume that it's like some Gaussian distribution. Maybe you're just missing a term. How is it that the Kalman filter doesn't go like, oh, I should correct my model? So what I like to think about the discrepancy model is basically saying, I'm going to make a better Kalman filter. So the Kalman filter should be engineered to say, like, if I'm always off in in a prescriptive way, a deterministic way. Maybe I could learn a model from that, improve my model. So I always think about the error in the model is you have a model, you're probably missing some physics, but then you do still have some noise. So at least you should be able to improve the piece that is like some kind of discrepancy that's deterministic. That's where I think this can work. And then you use GP on the rest. But just to say GP everything when it's in fact deterministic feels a little crude to me.
Mm-hmm.
So, but we still would need even to learn how to do a coordinates. Maybe even you can improve your coordinate system with this. We haven't played around with that very much yet, about also improving your model and your coordinates simultaneously.
Yeah. And in some way, the way you presented this, since the known part gets lumped into the data, probably just even plotting the data would reveal some of that structure, right?
Absolutely, right? And, you know, first of all, you'd probably see that, oh, it's not mean zero. Like this is always the assumption. If you look at the discrepancy, it's just some, oh, mean zero, you know, I'll fit a Gauss into it. And you'd right away see that, oh, it's not that at all. So that means there is some kind of underlying process to put in there that could be, you know, I think the goal is always to build a model so that eventually what you see at the outcome is a Gaussian distribution. Like, oh, that looks like noise now. That looks like just white noise sitting on top of a better model that I have now.
Yeah, and that I think reminds me also a lot about work in, say, image processing also, when you have, I mean, linear inverse problems with additive Gauss is a very, very standard thing. And then all the parameters are basically being tuned until the residual image actually looks like white noise.
Yeah, yeah. And, you know, look, generically, and I think all of us are guilty of this a little bit, right? When we don't know stuff, I actually heard this from somebody at a conference, I can't remember exactly where, but like when we don't know stuff, we just say like, oh, well, the stuff I don't know in life is, you know, mean zero and some variance, right? So you just say it's Gaussian. And I think the goal is we can do better than that, right? And I think we have the tools to do better than that. And to eventually squeeze it down to like, well, if I really do just have some measurement noise, then I should eventually at some time squeeze this down to a very small variance mean zero thing process at the end.
Okay, great.
Oh, and by the way, one of the questions I have here from Nathan Traskas. I wanted to talk really quick, just make one comment about constraints.
Oh, yeah.
The Cindy architecture also allows for constraints to be put in. This is work, Steve Brunton had done this with J.C. Lazois, and they basically showed that like if I have fluid flow and I know there's conservation of mass, you can actually, again, the beautiful thing about doing the Cindy modeling is it's an AX equal B problem, and then you can just put a linear constraint on that. So it becomes a constrained optimization, but a very simple form. And so you can actually say, find me a model such that conservation of mass happens, or impose conservation of mass. And so it will do that very easily with a subject to line off that AX equal to B solve. So pretty flexible framework. And I like the fact that you're solving AX equal to B, because that's about as sophisticated as I can get. So.
Great. So thanks for that clarification also. I've just been looking through the questions, and I think we've more or less covered all our bases. I would have one final question though for Nathan, since we have him here, and that's more, I want you to speculate a little bit for us, because in the beginning you had this fight kind of, or this two different viewpoints of Newton versus Kepler and data versus physics. So where do you think this will leave us as a field of people who are interested in both of these areas? Is there a middle ground, or are these extremes? What's your take?
That's a great question, because I don't know what the resolution of this is. I think the very fascinating thing about that graphic around robots and self-driving cars is they're both autonomy vehicles, and they have taken just in some ways, completely divergent paths for solving these very hard problems. My feeling is the ultimate success of the car and the ultimate success of the robot is going to mean that they're going to have to kind of move towards each other a little bit, right? So the robot physics is going to have to say, well, I need some flexibility of what just this data-driven modeling is, because, you know, again, discrepancy modeling is a great example where every robot on the Boeing factory floor is different in their discrepancy. Mm-hmm. And so you have to have a flexible framework that learns discrepancy models for individual robots. So use some kind of architecture which is a little bit less constrained by models to say, let me just build models as I go along. Whereas the car, I think you should imbue it with some physics, right? Besides rules about braking and acceleration and just don't hit things. I think that if the car was physics aware, I think it'll eventually have to be at some point. But it's hard to know when this will come back. The fact of the matter is, both industries will probably be in our future. You can imagine both industries just being billion and trillion dollar markets. So, you know, their goal is just to make it work. Their goal isn't to like, hey, let's bring this all together. So that might just take us as mathematicians, right, where we're not necessarily making the trillions of dollars, to come back over and say like, actually, we can connect these things together. But that's going to be a while, I think. But, you know, even just understanding more, I think what I love about this workshop and where we're going to go with things is that we're really trying to get down to, okay, can we just understand this fundamentally from a math point of view? Because I think that's going to allow us to really take advanced steps going forward. I mean, once you understand even things like, here's all these things I know to be true about Sturm-Liouville theory, then you can go solve all these physics problems based upon this really canonical understanding of this underlying mathematical structure. And I think that's kind of what we need next to figure out how this is going to evolve. So I think everybody here is going to make an impact. I'm excited at that.